If you're a developer, I'm about to share the one mind hack that keeps me and every solid engineer I know in the job market, doing work that remains meaningful, keeping skills that remain current with the insane wave hitting the industry right now. Understanding the 17 layers of abstraction between your physical machine and the features you're shipping every week. They're fundamental. Of the 17 layers, there's maybe 5 that most engineers could just name off the top of their mind. But by the end of this video, I want you to become a better engineer. If you're not aware of some of these or haven't considered this way of thinking about them, my hope is that by the end of this video, you become a better engineer capable of achieving way more. And the stakes just got higher to understand these 17 layers because one of them is intimately affecting the others now. As a modern engineer, you're the one who has to verify whether this new layer is producing the right results. I'm going to walk through all 17 layers in order, fast. By the end, you'll see which skills are going to matter and which ones matter most as things shift. So layer 1 is raw physics. Everything starts with the physical world. Electrons moving through materials, heat, noise, signals that degrade over distance. Nothing is naturally orderly, and nothing is built for binary at this scale because it's messy, it's analog, it's governed by laws that just, they don't care about your deadline. The best engineers that I know have a very solid mathematical foundation and know how these mathematical laws and models of physics allow for the rest of the layers to work. You do not need to be a physicist, but you certainly can't ignore physics entirely when it's the foundation of our reality. It's not just the ability to think critically and use data science when necessary. It also helps you stay grounded and understand the foundation of electronics, power consumption, and just first principles behind how humans establish infrastructure for the rest of these layers. This is first principles thinking. Layer 2. The transistor. By 1947, our understanding of physics was mature enough that 3 people at Bell Labs built the first transistor, which it changed everything because now you have a reliable way to represent binary state in the physical world. But one switch obviously doesn't compute anything useful on its own. You do need to combine them into something that processes multiple binary inputs to achieve one or more binary output. This brings us to layer 3, which is logic gates. When you wire transistors together into logic gates, physics starts obeying rules that George Boole wrote down in 1854 as pure abstract math. It was nearly a century before anyone had really had any hardware to run it on, and Claude Shannon was the one who saw a connection in 1937 and proved you could build Boole's logic out of electrical circuits, which is genuinely one of the most important bridges ever built in computing. At this point, abstract math is no longer theoretical and becomes something a machine can actually execute far faster than the mechanical limitations that were used in other forms of physical computation. But logic gates are stateless. They just react to whatever inputs they're getting in the moment. There's no memory attached. This means we need layer 4, sequential circuits. When you feed the output of a logic gate back into its own input through flip-flops and registers, and now the circuit can hold state across clock cycles. It remembers, and that's when computation outpaces humans. You now have millions of reliable states, chunks of data that transition and happen every single second inside a system that just doesn't get tired. It doesn't lose its place. But even if we have that, a circuit that remembers is still fixed. It does one thing, and when you want it to do something different, you'd have to physically rewire the system. But we can get quite far with just this, just using logic gates. You can build amazing things. Layer 5 is the CPU. Von Neumann proposed the stored program in 1945. Instead of hardwiring behavior into the circuit, you store instructions in the same memory as data and build one general purpose machine. And that reads those instructions and executes them for you. That's the CPU. And it's the first massive compression in this story. Messy, unreliable physics got turned into this reliable symbol processing machine that you can just do anything you can describe as a sequence of operations. Everything above this point depends on that hardware working. Programming a CPU still means raw binary. Opcode after opcode. Humans, they can't track or sustain that much complexity at the scale that we need to compute. This brings us to layer 6, the instruction set. The instruction set architecture becomes a fixed documented contract between the hardware and writing software for it. Move this register, add these values, jump to this address. Basically, it's just the machine's API. The reason it matters so much is that without a stable interface like this, every single piece of software would just be wired to one specific chip. That's not very modular, obviously, so the ISA is what lets software survive across entire generations of hardware. You swap the chip and the contract can just still run everything that you want it to run. So even though we have this with a documented instruction set, you're still thinking entirely in machine language. Whatever this API is, you're writing raw opcodes, and that's pretty brutal for anything beyond trivial programs. So if we want to increase the level of complexity here and not have to worry about some of those overwhelming things, we have to bring in layer 7, which is assembly. Assembly language gives you mnemonics instead of binary encodings, so you have MOV, ADD, JMP, representing the same operations for move, add, jump, but now a human can actually read what the machine is doing. This is the first time in history of computing that an engineer could actually look at a program and follow its logic, which meant you could debug and reason about it and teach it to someone else. Before assembly, programming meant raw numbers. After assembly, an entire profession became possible. So layer 8, high-level languages. Now, for you, you might think of a high-level language as something else, but these are languages that were thought of as high-level. John Backus at IBM created Fortran. In 1957, Grace Hopper's team created COBOL in 1959, and for the first time you could actually write loops, functions, algorithms in something resembling human thought, while the compiler handled the translation down to assembly. This is where programming was no longer just a hardware skill, and it really became a form of thinking that you could just express a calculation or business rule without really knowing which registers to use, and that took the number of people who could write software from hundreds to literally millions. But each language was still tied to a specific machine's compiler, and none of them gave you fine-grained control over memory that you'd need to really build something like an operating system. So this is where we hit layer 9, C. Dennis Ritchie at Bell Labs created C in 1972, and it hit this remarkable sweet spot. You could write once and compile anywhere there's a C compiler. Linux, Windows kernels, most databases, most networking stacks trace back to C. It's highly performant if you understand this language. So engineers who deeply understand C tend to understand where the cost of every higher layer actually comes from. But the problem with C is that humans can quickly become overwhelmed with the amount you have to track in memory, and it just gives you enough rope to hang yourself with in a way. Manual memory management has no built-in safety nets. And as programs got bigger, the bugs just got way worse. Buffer overflows, you had dangling pointers, memory leaks, and they surfaced under load. Organizing a large codebase in C is really painful. No real module system, no encapsulation, no hierarchies, so this brings us to layer 10. Type systems, objects, modules. Structured programming emerged, then object-oriented programming. Smalltalk in the 70s, C++ in 83, Java in 95, and the core idea here was to organize code itself so that types catch mistakes before runtime and objects can bundle data with the behavior that operates on it. Modules let teams separate a piece of a code base without constantly stepping on each other. This is where it's not just a one-person game, and you actually can start to grow a team of engineers who each have their own responsibility and can communicate about the code and focus on different things. You can start to build boundaries in the code, and it just allows you to coordinate and move beyond the nightmare that was present with the previous layer alone. But even with this better organization, most of these languages still require you to manage memory by hand, and your compiled code still only runs on one specific operating system. So we did have to hit this layer 11. A lot of people don't like the way this layer is. For some reason it's frustrating to them. It doesn't feel pure. But layer 11 is managed runtimes. Java's JVM arrived in 1995 and .NET's CLR in 2002, and they solved both problems at once. Memory gets garbage collected, so entire categories of bugs just disappear. No more buffer overflows, and your code compiles to bytecode that runs on a virtual machine, so it's portable across different operating systems. The trade-off is real though, and development speed increases, but then you lose direct control over how the machine allocates and frees resources, and most engineers never notice that trade-off until performance really starts to matter, at which point it can matter enormously. But even with managed runtimes handling memory and portability, you're still writing imperative step-by-step procedures for everything, retrieving data, provisioning infrastructure, and you're configuring entire environments where it's all manually orchestrated. There has to be somebody that knows what's going on at all times. This is where layer 12 comes in. This is declarative systems. Edgar Cogg published the relational model in 1970, and by the late 70s, SQL was implementing it. And then decades later, infrastructure as code arrived. We have Terraform, Kubernetes, CloudFormation, and the fundamental shift here is the same in both cases. At this point, you're not telling the machine every step that you want it to do. All you have to do is describe what you want to be true, and then something else will just figure out how to get there. The database optimizer decides how to retrieve your data, and the orchestrator decides how to schedule your containers. You get massive leverage from that delegation, but you also lose the visibility into the execution path. Even with better languages, better runtimes, and declarative tools, you're still building one program. But real systems, if you want to break things apart modularly, they have to be more than one program. There has to be boundaries between these things. You have to modularize these systems. They have teams, deployments. Code structure alone doesn't solve any of that. This is where layer 13 comes in, architecture. It is no longer about code structure, and it starts to become more about this concept where you can bring structure to the abstraction that really can compound over time, over years. Like, a bad architectural boundary doesn't show up as just a regular bug. It can, but it shows up more so as every feature taking 3 times longer to create than it used to. This costs businesses sometimes upwards of millions of dollars every year. Continuing to this day, architecture remains a skill that not every engineer has established well and understands enough to avoid these high-cost mistakes. It pulls in teams that don't need to be involved. It requires hiring outside experts to come in and review your system. In modern software engineering, there may be forms of architecture we haven't even discovered yet. Engineers who understand architecture and constantly learn architectural principles can see the difference between systems that suck your time away and systems that are adaptable and operate with a business, allowing objectives to ultimately be achieved in a timely manner. But even if you master everything there is to know about modern software architecture, there's still notoriously hard to communicate decisions and concepts. There's patterns to be found among different architectural ways of thinking. 2 engineers can look at the same system and describe it in completely different terms. They could make up different words for it. Teams do need some kind of shared vocabulary to reason about recurring structural problems. without re-deriving everything every time they want to communicate from scratch. This brings a human element into the mix where in layer 14 we have design patterns. The Gang of Four published their design patterns book in 1994 and gave teams a shared language for structural decisions. The entire point here is having a tool for communication, having the right pattern for the right situation, and understanding those trade-offs is a different skill. Just knowing that there's terms for concepts is highly useful for engineers. But most patterns assume your system runs on one machine. And by the late 90s and 2000s, that assumption stopped being true for a growing number of real systems. So this is where layer 15 comes in, and we have distributed systems. Distributed systems are the machine no longer being just in one box. We have the internet, and the truth is spread across networks, and messages can arrive in different times, and we can't trust or understand or know the exact time frame everything will happen. Clocks will disagree, services can fail partially, data can go stale between reading different elements of what the system needs to read, and these retries can create duplicates. This can become a huge issue. Your local intuitions about that order and that consistency and failures, they're just no longer reliable. But even if you have this layer, even if you have a solid understanding of distributed systems and you can solve a lot of these issues, building distributed systems from scratch every time is impossibly slow. You need platforms, pre-built components, and that lets you stand on other people's work. That can be a little dangerous too, but this brings us to layer 16, the modern platform stack. Frameworks, packages, orchestration cloud providers, APIs that connect everything. A single modern application might pull in hundreds of packages and run inside a container managed by an orchestrator, deployed to infrastructure, defined in code behind a load balancer, configured by a cloud provider. Each of those layers is someone else's abstraction. And when it all works, you ship faster than any previous generation of engineers has been able to. And when it breaks, you have to debug across all these layers you didn't even write, you didn't configure, and you may not fully understand them. And the pattern holds all the way through. There's more abstraction, and when you have that abstraction, that gives you more leverage. And it also puts more distance between you and what really is going on between these layers. But even with all 16 of these layers, the bottleneck was still implementation. It takes forever to set all this up, and you have to have experts that have done this and have lived through the layers and understand them well. An engineer's day before layer 17 was still mostly spent writing code and gluing all these pieces together and producing the implementation at hand here. So this is where layer 17 comes in. This is where communication in your own human language becomes a key skill, not just with other humans, but with the machine directly. This is not just a better autocomplete. This is an entirely new interface. Over implementation itself, you have to describe the constraints, explain the context, and verify that what it's producing is actually what you want. The reason this layer is so critical and so hyped up is because it changes where the bottleneck is in engineering, given all the skill sets engineers already have. Because this layer carries within it skill sets the engineers took years to develop. This includes general reasoning capabilities. And even to the very companies producing this technology, it's not fully clear where the bottleneck lands next, because agents seem to be able to reason so clearly on almost any technical subject you throw at them. Given the right context, it's unreal. But the bottleneck moves to whether you specified the right problem in the first place, whether you're actually aware of what's going on as a human. Because if you're not aware of what's really going on, what problem you're even solving in the first place, you're just producing prompts that feel like rolling the dice. The bottleneck moves to whether you can actually verify the output actually works or not. and whether you understand the system well enough to catch what the tools get wrong. As humans, we always are the final judge of whether the result is what we actually want it to be. That's not a future prediction. That's what's happening right now. So what sits above layer 17? I have no idea. But if you followed through the pattern through all 17 of these layers, there's an implication here, and that implication is very clear. Every single time a new layer appears, the scarce skill moves up the chain. The thing that was hard before gets automated. It gets compressed. And then the new hard thing becomes whatever sits on top of that. So right now, what sits above layer 17 for us to focus on right now as engineers, I believe are 4 main things. I break this acronym into CCVV: communication, comprehension, verification, and vision. Software has always been a coordination problem. You have to extract real requirements from messy human situations, explain trade-offs clearly enough that teams align on what matters. And now you also have to communicate with the machine itself clearly enough that a context window can absorb your intent and produce something useful. But the point of all this is not to just memorize the 17 layers. The point is that software has been climbing this staircase for decades. Each and every single one of these steps was a real solution to a real pain, which hid complexity and added more leverage at each point in a very fundamental way. Right now, there's a lot of types of implementation that are getting way cheaper, way faster, but that's not nothing. There's still somebody who has to orchestrate where we put energy into computing these outputs that we need, these tokens. We have to have people engineering the context. The engineers who stay valuable will be the ones who understand the full stack well enough to verify what comes out of it, think in systems, communicate clearly, and connect what they built into something that actually matters. That's the shift, and it's already happening. In the next video, I want to go deeper on those 4 skills, what they actually look like in practice, and what really separates the people who have them from those who don't. Thanks for watching.